program, but we'd love to see you there. Now we have the slide view.
Got it all?
Got it all.
Good to go?
Leaning back for a good show.
All right. Thanks so much. Thanks, everybody. Really appreciate you taking the time out late afternoon. Suzanne, thank you for that introduction. It's tough to live up to, but I want to share some stuff. This is work that I've been working on this stuff since about 1996. So it really represents, I'll show you the high points from some of the more recent stuff, but it really, I think for graduate students and faculty who, especially young faculty who might be listening in, I think it's kind of an example of taking advantage of an opportunity that was when I was at University of Texas. There was this group that was working on this cool satellite, the satellite mission itself fell into the sort of the sweet spot of my career, so I could start before the satellite was launched, and then put in all this time with graduate students studying all the feasibility, and then getting to having the good luck of the satellite working really well, better than we thought, and so getting these results and being able to share them with you today. So kind of fun, but there's a I don't know if I call it a downside, but there's a very urgent message that comes with this work that I want to share with you. And the punchline is we're in rough shape with respect to fresh water availability and how rapidly it's changing. And so that gets to this image that you see in the background. So I will start with a very simple definition of water security. So we're all on the same page, and then show you some of the highlights from some of this research, what satellites are telling us about water security in particular, how fast, how quickly some of these areas, their total amount of water available is changing. And then get into some implications. Suzanne was talking about the sort of the public side and the public discourse and getting engaged and trying to share the message. So I have some experience there I'd like to share with you, including some of the implications for what we need to do, and then what we're going to do about it. The short answer to what we're going to do about it is I don't know, but we're working hard here at USask and around the world, trying to work on solutions for global water security. And I use the air quotes because it's a tough problem. Okay, so simple definition of water security. I use a definition that sounds something like this. Can a region provide a reliable supply of potable water to its population to do all the things that it wants to do, both now and into the future? So all the things that it wants to do: grow food, water for the environment, water for people, water to produce energy, water for economic growth. These are all sort of competing uses we have to deal with today. So reliable supply, meaning, climate change is happening pretty fast, and water is being delivered at more, it's more variable, more changing extremes, more flood, more drought. Absolutely true here on the prairie. So that makes the job of the water manager much more difficult. So reliable supply, potable water. Of course, we need water to drink, but we don't always need to use the highest quality water, for example, to flush our toilets. So we can use water of different qualities, and we haven't really fully embraced that. And there's a lot of infrastructure obstacles to doing that, but we need to be thinking about that. So reliable supply, potable water, do all the things that it wants to do, I've already explained, both now and into the future. And that's, thinking about population growth, thinking about climate change. So if a region can do that, we say that it's water secure. That definition becomes much more broad now. We can add in all kinds of things like terrorism and protecting water supplies and access to water and on and on. But this is a simple definition I'll use for this presentation. So let's talk about some of the satellite stuff. It is pretty cool. I mean, I never really lose my excitement for talking about these satellites. So it's called the GRACE mission, Gravity Recovery and Climate Experiment. And so the first phase ran from 2002 to 2017. And then the follow-on launched in 2018. And it's called the follow-on because it's basically just like the original GRACE mission. It's a NASA mission, and by calling it a follow-on mission, we were able to get it launched faster as opposed to a new science mission. We just made the argument that these results are so compelling. We're looking at what's happening with water on land, which I'll show you. We're looking at the ice sheets melting. We're looking at how ocean mass is changing. So we have to just keep going with these measurements. So we were able to launch the follow-on in 2018. So I say that it functions like a scale in the sky. So there's those two satellites there that you see in the picture. They're not very big. They're like maybe 3 meters long by 2 meters wide by 1 meter high. And they fly at 400 kilometers, and they're separated by 200 kilometers. And they, so they're, we call a tandem orbit. So here they are. Let's pretend my little USB drives are the satellites, and they are basically in a polar orbit. So they're flying over the poles. They're chasing each other around. And so when I say they function like a scale in the sky, it's for the following reason. The way these satellites work, they're not optical. They're not taking pictures of the ground. It's not like a giant telescope. They respond to mass changes on the ground in the following way. When those two satellites fly by a place that has, say, the Canadian Rockies, right? And there's been a monstrous snowstorm, that region has gained water weight, and it pulls the satellites as they fly by, pulls it down, and then the next one comes, it gets pulled down, right? And likewise, when the satellites fly by a place that's lost water, like you live in California, in Southern California, so like constant drought, that region has lost water weight. So it exerts slightly less of a gravitational tug. So when the satellites are flying over Southern California, they're doing this, right? So by keeping track of the ups and downs and the tiny variations in the distance between the two satellites, we're able to map the regions of the world that are gaining or losing water mass on a monthly basis. And that's what some of those images were that I showed. I'm going to put my satellites down now. That's what some of those images are that I showed you and that I'll be explaining. It measures the change, the delta in the total water storage, all of the snow, all of the surface water, soil, moisture, and groundwater together. If you want to split it up, say focus on groundwater, which I'll spend a fair amount of time talking about, we need other data. I'll explain that. So there's work to be done. It works at large scales, monthly time scales, and 150,000 square kilometers and greater. So it is not, in the vernacular, we'd call it hydroclimatology and not hydrometeorology. So we're talking about longer time scales, bigger areas. We're not able to say what's happening out behind the Bessborough, this afternoon, but we are able to say, and I'll show you, a graphic on this later. Here in this quadrant of southeastern Saskatchewan, or this chunk of the Saskatchewan River Basin, here's what's happening on monthly and longer timescales. And it's accurate to 1.5 centimeters equivalent water height. That means that the change in storage, in water storage, that can perturb, that make the satellite move up and down, is 1.5 centimeters spread over 150,000 square kilometers. So whatever that works out to in cubic kilometers. And in a region like Saskatchewan, that's not much, so it's pretty sensitive. But if you're in Saudi Arabia, then it might not work as well. So that's a GRACE mission. It's pretty cool. Oh, I forgot I had this picture in here. I was at the launch of the follow-on, and so that was a very moving experience because I realized that I was old and that I was passing this on to the next generation. In fact, I have a meeting with some former students who are working on some updates to some of our work that includes the new data next week. So here's an animation. I hope you can see it okay. So, we're looking at the Middle East now. And
we're still on the launch.
Oh, you are?
There we go. Now we've got it.
You got it? Okay, we're going to go from started at kind of blue-green, and we're going into red. And, we're watching this area dry out. So, that's are all sea over there, which we know is drying up. And we can kind of see this, steady drying of this region, mostly Turkey, Syria, Iraq, and Iran, but then it kind of wraps around and starts heading down the Arabian Peninsula. And about 60% of what we're looking at there is from the disappearance of groundwater, the mismanagement of groundwater, which is a common theme for what this satellite has exposed. So, I like to say we don't sit around and watch animations all day, although it would be fun. Here's what the time series looks like for its Western Iran. And so this, this is sort of what the normal data look like. So each dot here, each point is a month. And we're looking at, these are actually anomalies of storage. So we're looking at wet season, dry season, wet season, dry season, wet season, dry season, right? And this trend is, an unfortunate downward trend that has been going on for some time and can be traced to a combination of the drought and excessive groundwater use. Sadly, this is a story that we see around the world. So let's look around the world. So this is a paper that we wrote in 2018. It's an example of it. I have one more example. Actually, I don't think I have it in here. I should have put it in. I took it out for another presentation and forgot to put it back in. But there are a couple of papers that we kind of waited to publish until the end of the mission. And this is one of them. And so this looks at almost all at the end of the first mission that the data wrapped up in 2017. So we published this data in 2018. And this is a map of the trends of over that time period, 2002 to 2017, the places that get wetter and the places that get drier. And so let me break it down for you because it always scares the heck out of me, and it's my job to, not that I want to scare you, but I want to raise your awareness. So red places are drying out and blue places are getting wetter. So, the biggest signals that we see are from the ice sheets, Greenland and Antarctica. Antarctica is actually melting away. It's just that weird projection, right? So the ice sheets are melting away, driving up sea level rise about 3 millimeters per year. Glaciers, the alpine glaciers, and even into Western BC, those are melting away. So Alaska, Colombia, Peru, Patagonia. We've got these broad patterns that are expected to, we think that they're climate change related, and I'll explain that in just a minute. But, the high latitudes getting wetter, and the low latitudes getting wetter. So the wet area is getting wetter, and the dry areas in between, the mid-latitude drying, that's what we see in yellow, the dry areas getting drier. So we think that one's driven by climate change. We hear about the extremes, the increasing intensity of flooding and drought, and that's starting to show up in the maps. So upper Midwest, Orinoco, West Africa, Okavango, Indian monsoon, droughts, right? So Athabasca drought, Brazil, Chile, Argentina, Madagascar, right? So these extremes are so severe, right? And we're so prolonged in these cases that they have an impact on this map. And then there's the one where I spend an awful lot of time thinking about, and it's the disappearance of groundwater. And these are some of the world's major aquifers. I'll get back to this in a little bit, but one of the I think real major contributions of the GRACE mission was to really expose the global and quantify the global nature of groundwater depletion. And I've taken it a step further, sort of talking about what it means. So all told, here's this picture. A lot of stuff is happening there, and I find it a little bit frightening myself. So the climate change thing I was talking about, the wet area is getting wetter, and the dry area is getting drier. This is something that has been predicted in almost all of the IPC, going back to the earliest IPCC reports. This is one from 2000 AR4, showing patterns of precipitation change, right? So you see high latitudes, low latitudes getting wetter, mid latitudes getting drier, but predicted for the end of the 21st century. And I used to ask, are we seeing it now? And we finally wrote the paper and said, yeah, we're seeing it. So we're seeing, these are the background trends in the dry areas getting drier, so the mid latitudes, and the wet areas getting wetter. So that's some pretty scary stuff. And these patterns, I'm sorry to say, oh, let's talk about Canada. Wait, okay, I'll get back to that punchline. I'll just share it with you now. The patterns are not changing. Okay. The stuff, there's aspects of the map that are fixed, like the high latitudes and the low latitudes. And of course, the glaciers are staying in the same place, and the ice sheets are staying in the same place, and all the aquifers are in the same place. Some of these spots that are related to interannual variations are moving around. Okay, but there's a broad fixed pattern that is very much climate change driven. Canada, well, we got the Alaskan glaciers, but we're also actually, that one I picked off is actually in western BC, near the Okanagan. I don't know if I have the arrow in the right place, but when I pulled the data out, that's what I wanted to try to get. Here's this Athabasca drought, also a place where, it's a fair amount of water use for the tar sands. As we get closer to Greenland, of course, that stuff is just melting away. And then along the bottom here, we've got places that are gaining water. So the head of the St. Lawrence here around Toronto. And here's this big spot that I've been watching for a long time. And, we live in this spot now, okay? I've been watching it for a long time, and we'll get back to it. For the longest time, it's just going up, 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 until now it's actually starting to go down. So I'll get back to that. I might get back to it right in the next slide. Oh yeah, here we go. It's right here. It is. So yeah, just looking at what's going on locally. So this is a time series for the whole Saskatchewan-Nelson Basin. Same sort of thing as that one I just showed you, is almost the same time series. So we see, sitting in that blue, fair amount of it, at least the western part, and maybe to the middle of Saskatchewan, is sitting in that big wet spot. So going up for a long time, but now starting to go down, and we should try to understand what's going on there. I have a student, David Ferris, who's told me he's looked at some of the groundwater well data before he saw this. He said, I always thought that, we were getting wetter. And then I started looking at some of the recent data, and it's starting to go down. And I had just looked at this in the morning, just coincidentally. And so shared this with him. And here's a different way to pull out the data, not by basin, but by this square here. That's in, roughly includes Saskatoon. Basically the same picture, right? So going up and then starting to drop off. So we need to pay attention to what that means. And it has implications for the whole irrigation thing that we've been talking about. And let me just segue into that. And by that, I mean the irrigation expansion on the prairies here in Saskatchewan. And so we can see that we've been increasing food production for a long time. It's showing up in this satellite map. This is a satellite called MODIS. It's a NASA satellite. And so this darker green means there's more. In this case, it's greening, but it's agriculture, right? So it's upper Midwest and into the prairie. So we're big ag regions. And so we're showing up as some of these top regions around the world that are greening up. And we also know that increasing mean temperature change will increase the growing season. So it's going to allow for even more food production. So we're already doing more, and the warming is going to increase the growing season length and allow for even more food production. So this is just as temperature increases, how many extra growing season days will we get? So what I'm getting at is that we're going to be stressing our water resources even more, right? And so, however, Canada's water supply is becoming far more variable. So can we match well, let's put it this way. There is a challenge to match the food production aspirations with the water management under climate change. And that includes changes to the timing of the water delivery, by that I mean melting of the snow and how it flows to the Saskatchewan River, and changes in the variability. So many of you on the listening already know that Canada is warming at twice the global rate, and the prairies in Saskatchewan are warming at 3 times the global rate. There are changes expected in precipitation, expected to increase overall, although summer rainfall may decrease. The seasonal availability of fresh water is changing. And so what's happening is that more of the rain that's falling, and most of the source of the Saskatchewan River Basin is in the mountains, right? But what's happening in the mountains, so it's in the Canadian Rockies out west. And although we do call ourselves in Saskatchewan the West, I don't acknowledge that. I'm calling it the Midwest. Okay. Anyway, so what's happening in the mountains is that more of that precipitation is now falling as climate warms, will be falling as liquid precipitation and not snow. And so that means it's washing off the mountains and into the river sooner. Okay, so we don't have what we used to have, basically like a big freezer. We just freeze the water, and then it would trickle out more slowly in the spring and the summer, providing us a longer access to water. Where that's disappearing, right? And so what that means is that we are going to have, I don't know if I actually wrote it out here, but earlier peak flows, right? Because in the spring, because the water's not frozen, it just washes off the mountains into the rivers, and then it's all flowed through the system. So a deficit in the summertime when we need it for irrigation, okay? So mixed in with that, more flooding, more drought, more wildfire risk. None of this is pretty. More extreme heat, less extreme cold, longer growing seasons. I don't want to depress you too much, so I'll just go to the next slide. Okay, I'm just gonna do two things: shift to groundwater. And when I talk about water so energetically and enthusiastically, I actually work up a powerful thirst. Okay, then. Groundwater. As most people on this talk know, it's the water that's stored under the ground. But some people don't realize that it is the primary water source for over 2 billion people, and it may be closer to about a third of the population. I need to get an updated statistic. This goes back now probably about 20 years. We've been saying 2 billion people. It provides almost half the water for irrigation globally. Okay, so it's a monstrous source of water. And in many cases, it's non-renewable, especially as you go down to these deeper aquifers, these deeper rock units, right? So the stuff that if you're in contact with the surface, then the likelihood of recharge, you're replenishing the aquifers through rainfall, typical water cycle activity is very high. But as you go deeper, and especially if you go into these more confined layers that are deeper, it just, the water doesn't get down there. And so if we're pumping it out, nothing is really coming back, or the amount that's coming back is just a, insignificant fraction of what's going out. So this is showing up in all of our maps. So how do we get at it with this GRACE satellite? So here's an example again. I told you we've been at it for a while. And so we worked this out, how to do it before the satellite even launched, so this is actually, the satellite launched in 2002, but that's the publication date. We probably actually wrote this paper in 2000. And Matt Rodell's one of my first PhD students who worked on this, and we still collaborate. He's now chief of the hydrology lab at NASA Goddard Space Flight Center on the East Coast, or Washington, D.C. Anyway, okay, here's what GRACE is telling us. GRACE is telling us the change in all of this water storage, okay? All of the snow, all of the surface water, all of the soil moisture, all of the groundwater. That's what GRACE is telling us. In theory, we should be able to just rearrange the equation and subtract from the change in land storage the snow, the surface water, and the soil moisture. So graphically, GRACE is telling us this, right? If we're interested in this, the groundwater part, we need to subtract all of the mass change above the groundwater. And we do that, so we need other data. And so what data we use depends on where we are. So if we're doing a paper like we did in the Middle East, and we're focused on Syria and Iraq, we're not getting any information. And so we're using satellite data and whatever else is out there. Computer, we model it. We've got some pretty advanced computer models that we use that are pretty accurate. But I spent a lot of time in California. I'll show you a California example. Lots of data availability, so we can use reservoir data for the surface water, we can use the snow. There's a National Weather Service that has measurements of snow and puts out maps of snow water equivalent. So we get a very good understanding of some of these components that we need to remove to isolate the groundwater. So here's an example. We're in California, Central Valley, huge agricultural region, shown in green. You know, if you go over to Sobe, so I'm sitting in my office here in Innovation Place. We go to Sobe's at Preston Crossing. You walk in, you know, there's strawberries, you know, from like right over here, right? There's like raspberries from like right over here. Okay, there's avocados from, you know, from down here. There's walnuts and pistachios and almonds from down here. This part of the basin has just been taken over by trees. Okay, so we're using a lot of water to grow food and ship it all over the place. Okay, and in the case of California, in a lot of our food producing regions, we use more water than we have available. And that's why these things start to show up as these red spots on the map. So here's the time series for the total, right? And so we want to, from this, so this is all the change. And so you can see, just want to point out, these are periods of the major droughts in California, that I lived through. And they were pretty difficult. And there were also a lot of fires and a lot of water restrictions. 2006 to 2010 and 2011 to 2016. Hot as hell, by the way, too. I mean, it just got ridiculously hot. So, you know, to get at the groundwater, we've got this time series of the total water storage, the snow, the surface water, the soil moisture, and the groundwater. So if we want to isolate the groundwater, we have to subtract the surface water, the snow, the surface water, the soil moisture. This is actually, we're just about to submit this paper. So this is our latest look at what's going on in California. So this is a groundwater time series, a remotely sensed groundwater storage change time series for the Central Valley here, shown in green. And what you see, and I'll show you in a second, is really part of a very long-term, I don't even know if I'd call it a water management strategy, but it's what happens. When there's a wet period, farmers can rely more on surface water, and so the groundwater recovers. And when there's a dry period, farmers rely more heavily on groundwater, and it gets depleted. And then in a wet period, right, a little recovery, and then in a dry period, a lot more groundwater use, right? And so there's this sort of like, it's like I call it like a tennis ball bouncing down the stairs. Just, you know where it's going. So we put it in this long-term picture that combines the GRACE data, shown in blue, with the US Geological Survey, shown in red, going back to 1962. And honestly, this time series actually goes back to since the beginning of irrigation in the Central Valley, which is like 1930 something. Okay, so it's like the cumulative loss is like double what we're looking at here. So we are looking at cumulative groundwater loss going back to 1962. The colors in the background represent what I was just talking about. Is it a wet period, shown in the dark blue? And we see some recovery. Is it a dry period, shown in the dark tan? Then we see these big depletion phases. Okay, the lighter colors are moderately wet, moderately dry. So again, it's this, right? It's been going on forever. And the part we've been seeing here with GRACE is just this part down the end. This is a huge problem, right? And it's happening all over the world, but just some examples of what's happening in California. Of course, the water table is dropping. Middle of the Central Valley, average water table depth is about 2,500 feet. Okay, to dig a new well, say, that is 2,500 feet deep is something like $1.25 million US. And so like, I don't have that money. You know, you probably don't. Suzanne probably has that money, but maybe no one else. And right, so access is now becoming a problem, right? Imagine you're a farm worker working on a big farm that grows pistachios and walnuts, and that farm is using all the groundwater, and you can no longer afford to dig a well to access that water. The ground is subsiding at the peak of the drought, not everywhere, but in places that have clay minerals in the aquifers, subsiding at peak rates about 1 meter per year around 2015, 2016. Think about that, 1 meter per year. not everywhere, but in sort of broad regions. There's all the ecological damage. There's the stream flow depletion that goes along with that. Of course, the water quality drops as you go deeper and deeper. It gets more total dissolved solids, more saline, on and on. So not good. To make matters worse, as happening all around the world. So these are some of the other aquifers that we've looked at a few of these in papers, and my colleagues have looked at several others. And, to make matters worse, they're sitting in these places that are getting less rainfall. So we're depleting the aquifers, and the potential for replenishment is decreasing because we're in the dry parts of the world that are getting drier. So it means less rainfall, less opportunity for replenishment. When we take this map and map those aquifers take this data and map it to, or just snip out, use the world's major aquifers as a template. So just sort of map that last image to this template of global aquifers. These are like UN recognition of the 37 major aquifers in the world. Over half of them are being depleted. So something like 20 out of 37 are past sustainability tipping points. And here I just mean classic resource sustainability. We're mining groundwater. And some really stand out. There's some serious issues. India, Bangladesh, northwestern India. Some of these aquifer templates are too big. For example, meaning that the signal itself is smaller than the template. So when you look at the Ogallala or the High Plains aquifer here in the United States, clearly there's depletion that's happening, but it's really just in the southern part. So when you map it to the whole aquifer, right, the northern part is actually getting recharged. It's the southern part that has depletion. So when you average it, it's averages to not a big loss. So anyway, this is not good. Here's some of the time series. I wrote a paper in 2014 called The Global Groundwater Crisis that sort of points all of this stuff out. There's a real important issue here, and that is most of these aquifers underlie some of our biggest food producing regions. So, as I mentioned before, groundwater supplies about half the water for irrigation. So if our water security is at risk, the disappearance of groundwater puts our water security at risk. Therefore, our food security is at risk. And so those of you who know me and my interest in food and water and bringing those communities together on campus, this is why, right? This is why, because our food security is at risk, our water security is at risk. And as a water security person, I'm not going to move the needle on global water security without addressing and working on the food part of the problem, because the food industry, agriculture, food production, packaging, the whole thing, food systems, that's 80% of the water that is withdrawn from our aquifers and from our rivers. All right. What are some implications? Ain't good. The human fingerprint on the freshwater landscape through climate change, through ice melting, through the changing extremes and water management, and here I mean groundwater depletion, is a dominant force, is the dominant force that is dramatically changing these patterns of water availability. And they're happening fast. Okay, so the change, and with it, major threats to water and food security is happening way more than people realize. And I'm happy to have the opportunity to share it with a few more people and get the message out. It gets a little scary and frustrating sometimes when I think about the number of times I've given this talk and the lack of progress that's being made. And I'll get to that in just a second. Implications. Food producing regions are in a state of chronic water scarcity. It's not drought. I mean, drought comes and goes, okay? The chronic water scarcity part is that these places are using too much water. They're trying to do too much. It's like you are keep spending on your credit card. You keep dipping into your bank account. That's exactly what the groundwater is, right? It's like your big retirement account, big stash of money, water. It's been accumulating over, millions of years. And we're like burning through it. So we're in deficit spending. There are distinct classes of water haves and have-nots, and this is the access. And so that could be geographically. You could live in one of these wet areas that's getting wetter. You could live in Canada, we're a water have. Or you could live in Southern California, we're a have-not. I was a have-not. I moved to have. Or you could also live on top of or one of these aquifers where your well was fine until it wasn't. Okay. We really need to do some exploration of the world's major aquifers, really understand like what is the freshwater availability, how is it changing over time. We would have done this, if this were oil, if water were properly valued, this would have been done. Okay. And we can't go too much longer without doing that. Internationally, groundwater is a critical element of national and international water supplies. It always gets left out of discussions. The discussions are always about water in the rivers. Great example, Colorado River Basin, Western United States, right? 7 states, 7 basin states, and 2 countries, and I forgot how many irrigated acres. All the attention on the Colorado River Basin is on the river. And what's happening is the groundwater, especially say in Arizona, which is the southern, there's the upper basin, the lower basin. The lower basin is basically Arizona. All the attention on the management is on the surface water. The groundwater is disappearing. This is from a paper we wrote that came out almost 10 years ago now. The groundwater is disappearing at a rate of about 6.5 to 1, 6 or 7 times faster because no one is paying attention. And to get that message out is almost impossible. These are regional problems that require regional solutions. Look at the size of some of these spots, right? This is like India, Pakistan. This is India, Bangladesh over here, right? So they're crossing, look at the Middle East, right? Turkey, Syria, Iraq, Iran, Israel, Jordan, Palestine, Saudi Arabia. The size of the spots, right? Those are transboundary spots. And so, it's really important to get people to work together. We try to be a catalyst sometimes to do that in places that aren't, with little diplomacy, with places that are not actively talking with each other. And all climate change mitigation policy will benefit water security, right? A lot of what we're looking at is so climate driven. So, I'm from the water is climate camp. What are we going to do about it? So the GRACE mission showed us this, right? Showed us this really compelling picture of what the heck is happening. Okay, so it's a bad situation, right? But the follow-on mission is showing us that things are not improving. Okay, so here's when we wrote this paper in 2009, and things keep on that downward trajectory. Here's when we wrote this paper in California, 2011. We're about to write the second one. It's, going to submit it in a couple of weeks. Here we are. All right. Wrote this paper on the Middle East here, 2013. Here we are. Here we are here. And I was just talking about the Colorado River Basin. And to be honest, I think this is really going to drop off now because there's like really accelerated groundwater depletion happening in Arizona. I think that downward trend is going to accelerate. And the maps that I showed you, the aquifer map and the global trend map, they look the same. That's what I was saying about like these regions are all fixed and, they're drying out and they're, melting away. The groundwater is being depleted. So there's really an urgent need to do the regional and global science and engineering, but we have to, if we really want to move to solutions, we have to bring in the policy, we have to bring in the financial innovations. Okay, if we want to think about how to really, because we know what's going on, I can show you what's happening with the water. Now we need to do something about it. So, there are policy and management and financial tools that need to be applied. So we need to engage with the policymakers, the planners, the stakeholders, and the public to discuss the adaptation strategies and the science and policy needs. We need to engage deeply, right? So how can I go to, I see these hotspots and I've tried to visit as many of them as I can. How can someone like me help in Bangladesh? Well, you know what? You got to get over there and you have to engage with the stakeholders. I know that they don't really have the expertise to use these kind of data, but they can be used to help manage water. So we have to go there, develop the relationships, co-develop questions. Of course, always do the highest quality work that we can. That's our calling card. And we need to go a step further and to communicate the compelling results, right? So how do we communicate to stakeholders, to resource managers, to elected officials, and to the public? So this is a call for for more transdisciplinarity. We do need to integrate across disciplines. That's the interdisciplinary part, but across institutions and go beyond academics. That's the transdisciplinary part. Okay, there's no other way for us to get our research into practice and have impact. Try to end on a modestly positive note. Sometimes when scientists and the media and government all work together and stay on point, as happened in California in the early part of the 2010s, good things can happen, and you can actually impact water management. And you don't have to read all this, just focus on here. I'll just tell you that in 2014, California passed the Sustainable Groundwater Management Act, or SGMA, SGMA, the last state in the United States to pass groundwater legislation. But the governor's office and the State Water Resources Control Board were quite clear about the impact that the scientists in California, in University of California and all the different universities in California, and including some of us at NASA, Jet Propulsion Laboratory, had such a big impact, right? Some of those graphics that I've showed you, we had this killer, and I should have showed it to you, killer animation for California, like the Middle East animation. It just got so deep red that it just drew in, was Jerry Brown at the time was the governor. It just drew these people in. But it also enabled them to take the conversation to the public and say, listen, we have to do something about this. So that passed, and maybe there's more good news. So similar stuff is happening here. A lot of our colleagues, especially here at the Global Institute for Water Security, John Pomeroy is a guy who's been working on, water policy and pushing for a Canada Water Agency. And that's another thing, I think, another case of, university people, government people, coming together and actually being heard about the need for larger scale water management. So there's potentially more good news there. I could be done. I think I'm done. For more information, website, our Global Water Futures program, please, someone new, follow me on Twitter. And if you have not checked out this is our outreach platform that we've sort of developed over the last couple of years. We're doing a virtual film festival, movies about water, documentaries about water, new theme each month. We do a podcast, which I actually host. It's a little scary, but we had a very famous guest on our last one, episode of the season, Jeff Sachs from Columbia, who's a huge sustainability guy. And we're also doing, reaching out to schools and doing 2-minute short film competitions with, we started in Saskatoon last year, but now it's across Canada. Middle and high school students who do 2-minute films about water, and they can win cash prizes, not for themselves, but for their schools. I'm done. Thank you.
Thank you, Jay. I learned something a little bit more every time I hear this talk. It's just mind-blowing the first time you hear it. We've been pretty lucky this term about the people that we have for these ENGTALKS. AJ Delay gave the last one, and he had won a major national career award. I just put in the chat the very long title of the award that Jay received, which prompted my saying we have to get him to come and talk to engineering, because he is got a partial appointment in our college, and I'm really thrilled to have had you here today, Jay. I do want to open up the floor for any questions that the audience might have. Well, I officially congratulate you for winning the 2020 Hydrologic Sciences Award from the American Geophysical Union for outstanding contributions to the science of water over your career. We were
Thank you so much.
crushed that none of these big events happened in person this year.
Yeah.
But it's really a treat for us to get it virtually. And I know that we have alumni logging in from across the country. So we have a small but mighty crowd of followers with us today. And I'll just open the floor for questions. Feel free to turn on your microphone and or your video to tag Jay in.
May I ask a question?
AJ, please.
Jay, congratulations, and I really enjoyed your presentation with a lot of satellite data and very high quality work that you have been doing and contributing for the benefit of the not only for Saskatchewan, not only for Canada, not only for US, but for the entire planet. So again, congratulations.
Thank you.
My question is very, very simple. You mentioned about the Athabasca Glacier, and you mentioned it's a big freeze and water is coming, should be coming slowly to all the rivers for the benefit of all. Now it is giving out more water, more with high speed, more frequently. Is there a forecast on how unsustainable the water supply would be down the road, and when you see the crisis for the Midwest Canada?
Yeah, so there haven't been any long-term forecasts that I know of, although we do have the Canada's Changing Climate Report and the prairie focus part of that. I did not. The challenge with the future, especially like things like melting glaciers, is that stuff isn't really well represented in models. So it becomes really difficult to make those predictions. They absolutely should be done. Sometimes when people ask these questions, I realize like, oh my gosh, this is like so ridiculous. Of course we should have done this. So if people have done it, I haven't seen it, and especially about the issues of melting ice, right? And this is there have been studies, of course, in the Tibetan Plateau and, the time scale to the disappearance there. Just one more thing I want to add on that is that within our models, the modeling of how the ice melts and breaks up is not really that good. Okay, and so our models, especially when you look at the big ice sheets like Greenland and Antarctica, tend to be very conservative and tend to underestimate. Okay, so anyway, thank you for that. Thank you for that question, and I don't have the answer.
So is the Greenland deep red all about melting of the ice sheet?
Oh yeah.
Okay.
Yeah.
Okay. And I saw
melting mostly around the edges. It might be building up a little bit in the middle, but yeah, and it's a melting, and then now it's getting to a point where there's like the brittle breakup, right? So engineers understand this, and so like understanding that brittle failure, and then what happens when an ice dam breaks, and then you've got this acceleration from these ice rivers. All that is not really well captured in models.
Wow. Okay, Danella and then Vishnu.
Hi. You touched on this a little bit in your talk, or you alluded to it. The collaboration between the water security people and the food security people on campus with two major centers. Can you talk about what sort of collaboration is happening? given what you mentioned about agriculture being a big draw on groundwater?
Yeah, sure. So shortly after I got here, I made sure I met the food people at GIFs and got over to Ag Bio and met Angela. And so there's a few things that are happening. So we just had a workshop actually in November, and November 16th and 17th, and our report came out on February 1st. So it's still relatively hot off the press. So thinking about areas for overlap, projects, right, proposals. We're actually writing a create proposal together right now. And we want to follow up with more maybe seed money to seed projects and you know, position ourselves for grants in the future. So I can share that report with you, Suzanne. Maybe you can circulate that around to anyone who might be interested. But the other thing, you know, I mentioned Bangladesh, and so GIFs has been leading this effort to get over to Bangladesh and help on, you know, it's food and water. It's the usual, you know, genomics and phenomics, but also breeding with Leon coaching, you know, breeding, so, and working with us, thinking about water management, thinking about breeding for drought tolerance, you know, using lower quality water, more saline tolerant plants. So it's just a few things. So stuff's just starting to happen.
Just starting to happen and accelerating all the time. Vishnu Acharya is our new USask Ag Chair, and he's got a question in the chat. Very nice presentation. Does your model consider water pollution?
No. And I'll tell you what, we have a separate project on doing a global assessment of like major contamination and surface water pollution. And when we overlay these things, I think it's going to be really, really scary. So no, this is purely, you know, physics. It's gravity. It's called time variable gravity. It's really all about how the mass movements. It's really about how water moves over the planet. That's really what we're seeing.
I'm looking at the clock. I'm knowing that people have had lots of time in the box today. I also can tell you that if you want to tag in with Jay and talk about collaboration, share a coffee, do some good conversation, I'm sure he'd be up for that. As I said, we've got alumni here from both New Brunswick and Alberta. So I want to give a shout out to those people. We've got a number of associate deans, department heads, and graduate students. Thrilled that you could all join us today. Really exciting to have this work being done at the University of Saskatchewan, and the legacy of things that happen in space that we don't necessarily connect in really cool ways to really practical problems. So just thanks for sharing this tremendous bit of work with us, Jay.
Thank you so much. It was a pleasure. Thank you, everybody.
Applause.